Hello everyone, very good evening and welcome to the BYJU'S Exam Prep. Now in this session we are going to discuss analog circuit part 2, that is all formula in one shot, and it is a formula 1 series, right guys, and it is the second part of analog circuit, one of the most important subject for electronics, electrical and instrumentation branch. This is Sanjay Rathi. Let me know that sound quality, picture quality, everything is fine. Yes please. GATE Formula 1 series on analog circuit. Yes, please. First of all, inform me that sound quality, picture quality, everything is fine. Okay. Hello, everyone. Now, I think sound quality, picture quality, everything is fine now. Okay. Now, in this session, we will discuss important formula related to what rectifiers. That is rectifier, half wave rectifier, full wave rectifier, bridge rectifier, and then what clipper and clamper, right? And after that, we will discuss BJT biasing and stabilization techniques. Then MOSFET. After that, feedback amplifier and what oscillators. In previous class, we have discussed operational amplifier, multi-vibrator, that is bistable, monostable, astable multi-vibrator, and different types of symmetry triggers. An important formula related to symmetry trigger, square wave generator, and monostable multi-vibrators. So, in a previous class already I have discussed all this. Join my Telegram channel, that is Electronics by Sanjay Rathi, for PDF of part 1 and part 2. And today I will share the password for the PDF for part 1 as well as part 2 during this class. Right guys? Then it is a Formula 1 series part 2. And this is my small introduction. Myself Sanjay Rathi, and I am having around 21 plus years of teaching experience. I have qualified and selected for engineering services exam. My rank was AIR 16 in ECE 2005 and AIR 21 in ECE 2008. I have mentored more than 1 lakh students for these competitive exams, and these are my areas. Okay. Everything is fine now? Okay. Then this is for you, the GATE test series for GATE and ECE at affordable prices. You can join now CS, electrical branch, electronics, instrumentation, mechanical and civil engineering. Already we have around only 3 months for GATE exam, that is for you, and then 90% scholarship on preparation program on 29th October. Please note this time at 8 PM. Tomorrow I have one important session, that is a very important subject for electronics branch, that is EDC, electronic devices and circuit, all formula in one shot. Means I will discuss all the important formula related to semiconductor physics, then PN junction, then BJT, and then MOSFET, and finally special diodes. All the 5 topics in one session. Okay, all formula in one shot. That is electronic devices and circuit. Please note the time, tomorrow 9 PM on same channel. So subscribe the channel, like the session and share the link of this session. Okay guys. Now first of all, rectifiers. Rectifiers means 3 types of rectifiers, that is half wave rectifiers, full wave rectifier and what bridge rectifier. Full wave means center tapped transformer type. Okay, if you have any comments, then please give the comments. Okay then. This is a diagram for half wave rectifier. Watch this diagram carefully. Here one diode is connected. Here we are connecting the transformer. The role of the transformer is step up or step down the signal. Normally at this point we are applying the signal. So it is written as 230 volt, comma 50 hertz. Remember that this 230 volt, if nothing is given, that 230 volt is the RMS value. Okay. And convert it into peak value at this point. So it will become 230 into root 2. The peak value will be 230 into root 2. First of all. Second thing, after step down, N1 is to N2, that is the turn ratio. Here we are getting the Vm sin omega t. Normally we are writing Vm sin omega t. Remember that Vp by Vm. Vp is the peak value on the primary side and Vm is the peak value on the secondary side, N1 by N2. First of all, get the value of Vm. Why? Because all the formula will be in the form of what? Vm only. Vm. And that is the input we are giving. The input means this is the input at this point on the secondary side of the transformer. The value of the peak value of this input is Vm 0 and what? Minus Vm. Minus Vm. Now, at this point, always remember at the transformer side, on the secondary side of the transformer, the input signal is Vm sin omega t and RMS value of that signal. RMS value of the signal is Vm by root 2. This is nothing but RMS value of the sinusoidal signal. They will ask one question, what is the RMS value of the signal at the transformer side? Not at the output. I am talking about at the transformer side. That is the difference between what? RMS value of the output and RMS value at this point. It is the Vm by root 2. And what is the DC value or average value of this signal? 0. Because it is a positive area and negative area, positive area are equal. So DC value or average value is 0. Right? Now, we are connecting the diode and because of that we are getting the output at this point and that is half wave rectifier. So finally, you will get this type of output. That is the output of the half wave rectifier. And for this type of output, you have to find the RMS value, DC value, right? Ripple factor, form factor, crest factor. So remember that RMS value for half wave is Vm by 2. DC value is Vm by pi. Ripple factor is nothing but RMS value of the AC component upon VDC. Everyone give me the value in comments box. Form factor is the overall RMS value divided by VDC. And the crest factor is the peak value upon the RMS value. Peak value upon the RMS value. Ripple factor is also given by root over f square minus 1. This is nothing but RMS value of the AC component upon DC value. Right. These are the parameters related to rectifiers. Now, first of all, what will be the question? What are the ideal values of ripple factor, form factor, crest factor, right, for rectifier? So, after rectification, we want pure DC signal like this. Then the ideal value of the ripple factor is 0. Why? Because AC component is 0, so that RMS value of the AC component is 0. Form factor from this formula, if it is 0, the form factor is equal to 1, Vrms is equal to VDC upon VDC, cancel out. Peak is, that is the crest factor is also 1. Crest factor is also 1. These are the ideal value for rectifier. Ripple factor, form factor and what? Crest factor. These are the values. Now for half wave rectifier, ripple factor is 1.21, form factor is 1.57, nearly equal to, crest factor is 2. Rectifier efficiency, output DC power upon input AC power. That is another important formula. How much percent of AC signal is converted into DC when we are using some rectifier, and this efficiency is 40.6% nearly. For half wave rectifier, it is a very low. Another parameter is transformer utilization factor. Here we are using the transformer So what is the use of the transformer? It is a very bulky and heavy and costly device. So there should be a proper utilization of the transformer. So in case of half-wave rectifier, the transformer utilization factor is only 0.286. Right? It is underutilization. Right? Now, ripple factor is very high, form factor is very high, crest factor is high, efficiency is very low, transformer utilization factor is very, very low. So these are the points related to half-wave rectifier. And then we are using the full-wave rectifier. That is the full-wave rectifier. Watch this diagram. D1 and D2. Here it is called center tapped transformer type. That is the D1, this is the D2 and this is the RL. Here we are using center tapping. Now, full wave means at this point we are getting the full wave like this. In half wave we are getting this type of waveform. So what are the important formula related to full wave rectifier? Now, watch this. For full wave rectifier, ripple factor will become 0.48, form factor will become 1.11, crest factor reduces √2, and then rectifier efficiency ideal condition, it is 81.06%, nearly equal to, this is the rectifier efficiency, and transformer utilization factor is nearly equal to 0.69. This is the transformer utilization factor. There is improvement in efficiency, reduction in ripple factor, reduction in form factor, reduction in crest factor, and improvement in what? Efficiency of the system. So that is the factor related to full wave rectifier. That is the meaning. Now, PIV. PIV, that is the peak inverse voltage. This is VM for half wave rectifier. PIV is 2 VM for center tapped transformer type. Center tapped transformer type. That is the drawback of center tapped transformer type, that its PIV is high. And that's why it is not used for high voltage application. Remember, in GATE exam, there will be question like MSQ, multiple select questions. So they may ask theory, why we are not using center tapped transformer for high voltage application, or simply center tapped transformer type rectifier is not preferable for high voltage application. What is the reason? So that is the reason PIV is high. And that's why we are using bridge rectifier. The third one is bridge rectifier. Everyone please give me the comments that up to this point everything is fine now. Okay. Okay. Now next thing, that is the bridge rectifier. Bridge rectifier, that is the full wave rectifier. Again, it is a bridge rectifier type. This is the bridge structure, diode D1, D2, D3 and D4. Here we are connecting the RL in between D and C, and here we are taking the output. Here we can directly apply the input without use of transformer, or we can use transformer also. Means when we are considering a transformer, this type of diagram. Here we can connect transformer also. If transformer is not required, then we can directly connect the input also. So that is the two cases. First case, we are directly connecting the input. In second case, we are using one transformer here. Right? That is the biggest advantage of bridge rectifier. In case of center tapped transformer, we can't remove the transformer, because in case of center tap, the transformer will serve two purposes. First, step down or step up, or second, it will provide push-pull voltages. Because of this, when this diode is on, at the same time that diode is off. When this is off, this is on. And that is possible with the help of center tapped transformer type. And that's why we can't directly apply the input in case of center tapped transformer type. We have to connect, and this is a very costly affair. But in case of bridge rectifier, if the transformer is not required, we can remove the transformer. Right? What is the advantage of bridge rectifier? What is the advantage of bridge rectifier? The PIV, peak inverse voltage, is only Vm. And that's why we can use the bridge rectifier for high voltage application. High voltage application. So this is about the half-wave rectifier, full-wave rectifier and bridge rectifier. And this table is available for you. You can compare all the rectifiers. Please compare half-wave rectifier, the ripple frequency, the frequency of the output signal or frequency of the AC component at the output, that is called ripple frequency, is F, Vm by pi, Vm by 2, form factor 1.57, ripple factor 1.21, crest factor, PIV, transformer utilization factor. Second, full wave center tapped 2F, 2 Vm by pi, Vm by root 2, 1.11, 0.48, root 2, 2 Vm, 0.693. And in case of bridge rectifier, again the ripple frequency is 2F, 2 Vm by pi, Vm by root 2, 1.11, 0.48, root 2, Vm, 0.812. Means bridge rectifier, the transformer utilization factor is highest. That is 0.812. So that is the advantage of bridge rectifier over center tapped transformer type. If you want the PDF of all this, then please join my Telegram channel. I will share the link with you. Okay, everyone, please join my Telegram channel. That is Electronics by Sanjay Rathi. Okay, just yes, please. That is my link. That is Electronics by Sanjay Rathi. I will upload the PDF of this session with password. And for password, please wait for 10 minutes. I will share the password for analog part 1 as well as analog part 2. Then, this is the important parameters of the rectifiers. Now, filters. Here we are using the filters with the rectifiers. Why? Because after rectification, that this is the rectifier. Here we are giving the sinusoidal signal, and here we are getting half wave or full wave, but we are not getting the pure DC signal, and that is called pulsating DC. It has AC plus DC, AC plus DC signal, and the name of the AC signal is ripple. It is unwanted signal. AC plus DC, it is called pulsating DC. Pulsating DC. Now to minimize the ripple signal, we are using filter circuit. Very good evening, Piyush. Sorry, Payas, how are you? I'm Abdul Rajak. Right. Then it is not pure DC signal. Pure DC signal means this type of signal. Now to minimize the AC, we are using what? Filters. So there are different types of filter: capacitor filter, inductor filter or choke filter, L section or LC filter, pi or CLC filter, pi or CRC filter for compact circuit. Right? For GATE exam, one of the most important is what? Capacitor filter. Normally we are getting the question from capacitor filter. Right? And these capacitors are connected parallel to RL. Capacitors are connected parallel to RL and inductors are connected in series with the RL. That is the difference between capacitor and inductor. So watch this. This is the diagram, half-wave rectifier. Here we are connecting capacitor parallel to RL. Second important thing, the value of C should be as high as possible. As high as possible. Okay guys, this should be very, very high. Normally we are using in the range of 1000 microfarad. I am fine. 4000 microfarad or 4 millifarad. This is the very, very high value of the capacitor. So this is a very high. Second thing, another important question, another important formula, RLC, the time constant, that is the resistor and seed. It should be very, very high. It should be very, very high, and that's why this circuit is preferable for high load resistance. High load resistance. Okay. Lovely saying hello. You are new and this subject is new for you. Okay then. So there is a quick revision for GATE 2023. Right. So this is a Formula 1 series, and analog is a very big subject, and I want to cover the complete formula in two parts, that is part 1 and part 2. So that is the second part. In first part already we have discussed operational amplifier. Rectifier, yes, definitely, Banerjee. That is instrumentation analog is very, very important for you. Okay. So definitely you will get the question from that. Full wave rectifier with the capacitor filter, GATE, that is for GATE 2023 now. So already in case of half wave rectifier connected to parallel. In case of full wave rectifier again connected to parallel with the RL, that is the capacitor. Or in case of bridge rectifier, again the capacitor is connected parallel to what? RL. Now, what are the important formula? In case of half wave rectifier, when we are not connecting the capacitor, PIV was VM. But when we are connecting the capacitor, that is the drawback of this capacitor, PIV will become 2VM. With capacitor, PIV is 2VM. Without capacitor, PIV was VM. That is the disadvantage of capacitor filter. That will be the question. Second thing, the current will be very, very high. The diode current will increase. After connecting the capacitor, the diode current will increase, highly increases. In case of center tapped transformer type, before capacitor, PIV was 2VM. After capacitor, PIV was 2VM. It will remain 2VM. There is no change in PIV. Right? This is an important concept here. In case of bridge rectifier, what was the PIV before capacitor? PIV was VM. After connecting the capacitor, PIV will remain VM. No change. No change in the peak inverse voltage. Right. Now, ripple factor. That ripple factor in case of capacitor filter, inductor or choke filter, because this is a very, very important parameter. Right, you know, ripple factor is 1.21 for half wave rectifier, and for full wave rectifier it was 0.48 without capacitor filter. But there is improvement in that. This is the formula for ripple factor in half wave rectifier, 1 by 2 root 3 FCRL. A full wave rectifier 1 by 4 root 3 FCRL. F is the frequency, C is the value of the capacitor, RL is the load resistance. Right, load resistance. Time constant. Okay, Jai Surya. For capacitor filter, the time constant RLC should be very, very high. Why? Once the capacitor will charge up to any value, for example, let it is the charge up to 10 volt. Then we want this voltage should remain constant. So capacitor, ideally the capacitor should not discharge. That is possible when time constant is infinite. But practically it is not possible to keep the time constant infinite. And that's why RLC should be as high as possible so that capacitor will not discharge through RL. If the capacitor will not discharge, it will maintain the 10 volt. And we want constant voltage. That is the reason. It is clear, Jai Surya? Okay. Now, the ripple factor, capacitor filter, remember that what is the important thing I want to give. Here it is inversely proportional to F, inversely proportional to C, inversely proportional to R. Or it should be as low as possible. And that's why F should be high, C should be high, RL should be high. Here 2 root 3, here 4 root 3. This is very, very important. In case of inductor filter, but only remember that ripple factor is directly proportional to RL. And it is inversely proportional to frequency. RL should be as low as possible in case of inductor filter, and frequency should be as high as possible. That is the case. Okay, so this is the case. Now English batch. Okay, already I have started taking analog in Hindi batch. Then if I got the idea, then definitely I will inform you. Okay, then this is the ripple. No need to mug up the formula only, that mug up the concept only, that is, it is inversely proportional to RL 1 by F, and it is 1 by tau. That is, the time constant should be as high as possible. So what is the time constant in case of inductor? L by RL. L by RL. Tau should be as high as possible so that ripple factor will be low. So L should be high but RL should be low. So that is the difference between the capacitor filter and what? Inductor filter. So just I am concluding, and in case of capacitor filter, ripple factor is proportional to 1 by tau. That is, ripple factor is proportional to 1 by RLC. RL should be high, C should be high. In case of inductor filter, again it is proportional to 1 by tau, and it is proportional to RL by L. Then RL should be low, L should be as high as possible. Inductor is always connected in series with the RL. Series with the RL. Here inductor is connected like that. Or it is always connected parallel with the RL. That is the difference between inductor filter and capacitor filter. Now, so these are the two important formula. First capacitor, second inductor. Third one is L section or LC filter. In L section or LC filter, we are using L as well as C. L as well as C, right? So L as well as C means this type of diagram. Any rectifier, we are using inductor in series, capacitor in parallel, and that is the RL. That is the RL. Or in a pi filter, first of all we are connecting capacitor, then we are connecting inductor, then we are connecting capacitor. CL, C. What is the important here? Ripple factor is proportional to 1 by F square. Here ripple factor is proportional to 1 by FQ. So if suppose we are increasing the number of reactive element, ripple factor will reduce, because when we are using single element, R is proportional to 1 by F. For example, in C filter and L filter, if we are using the two reactive elements, 1 by F square. If we are using the three reactive elements, 1 by FQ. And because of this, ripple factor highly reduces. Okay. Okay, one by one I will give the answer for your questions. Is there is any doubt in this? Anyone? That is the formula for the ripple factor. Please go through this. L section or LC filter, pi or CLC filter. No need to bug up, but simply remember that it is independent of RL. Here it depends upon the RL. Previous two formula depend upon the RL, but this is for L section filter, it is independent of RL. Inversely proportional to L, inversely proportional to C. Always remember that. Okay guys, बोलिए जरा आपके क्या डाउट्स हैं? Acha, sir, for electrical student, how much analog preparation is enough? Subham Sri, for electrical branch, right? High frequency analysis of BJT and MOSFET is not so important, but almost everything is important, guys. Okay. Okay. So that is a rectifier, especially diode circuit, biasing and stabilization of BJT. Some questions from MOSFET and oscillators. These are the important topics. And the operational amplifier, application of the operational amplifier. Okay, that is. Now, this is all about the clipper, rectifier and filters. Now, clipper, second diode circuit. Clipper, when we want to limit the waveform, when we want to limit the amplitude of the signal, right, then we are using the clipper. It is also called as voltage or current limiters, amplitude selector, or what, slicer. The clipper is of two types, positive clipper and what? Negative clipper. Second classification is what? Shunt clipper and series clipper. Shunt clipper means when the diode is connected parallel to RL. This is the diode connected parallel to RL. Then it is called shunt clipper. When the diode is connected parallel to what? When a diode connected series with the RL, then it is called series clipper. Now negative clipper means when it will cut the negative portion, okay? Or positive clipper means when it will cut the positive portion. That is what? Peak clipper. Positive clipper means peak clipper. That is the point. Normally by using, in case of GATE exam, pi model or RE model, I will discuss here, okay? Okay. Sir, for BJT small signal model, which one is the following? Yes, yes. I am saying that pi model or RE model. In GATE exam, pi or RE is important. Very good evening, TRB Poly. Now, clipper. Clipper is a circuit that removes either positive or negative parts of the waveform. This kind of processing is used for signal shaping, protection and communication, and these are also referred to as voltage or current limiters, amplitude selector or slicer. That may become MSQ. A, B, C. Which options are correct? Okay, so that theory part. Now, positive clipper. The circuit remove all the positive parts of the input signal, then simply it is just like a half wave rectifier, because here we are not using any reference voltage. Then it will cut all the positive part and it will pass only all the negative part here. This is called positive clipper. Now, if suppose we are connecting a battery like this, VR, then what is the name of this? So there will be four options: shunt positive clipper, shunt negative clipper, third one series positive clipper, or fourth one shunt series negative clipper. This type of option on clipper. So it is a very, very simple thing. Suppose we are connecting VI here. When it is positive, definitely the diode is on. Definitely the diode is on. When the diode is on, definitely there will be the clipping. Definitely there will be clipping. So for positive portion, the diode is on. That's why the positive portion will cut. And that's why it is a positive clipper. And second thing, diode is connected in shunt with RL, and that's why it is called shunt positive clipper. Shunt positive clipper. Similarly, if suppose we are changing the polarity of the diode, it will become shunt negative clippers. Change the polarity of the diode. Change the polarity of the diode, and then the diode will be on for negative value of VI, and then it will become negative shunt clipper. That is the way. In this way we can understand the concept. For which portion the diode will be on. If it is on for positive, positive clipper. If it is on for negative, negative clipper. But just opposite here. If it is connected in series, my dear. This is connected diode here and that is the RL here. If I am giving the VI, for negative portion the diode will be on and for positive portion the diode remain off. When the diode will remain off, then there is a clipping. Then there is a clipping. So that is, for negative portion the diode is off and that's why it is a negative. In this way we can give the name of that. Or it is connected in what? Series with the RL. Series with the RL. So that is the simple way. Right? So how we can solve it? For no. When the diode is off, there is a clipping. If suppose we are making some mistake, then you can check here. Always remember. This is the case. This is R. Let this is the 2 volt. Here I am giving the VI. Now you can check. When the VI is less than 2 volt, when the VI is less than 2 volt, diode is on. Or when the diode is on, this will act as short circuit and output is exactly replica of the input 2 volt. Sorry, VI. Output is exactly replica of the input, that is the 2 V0 is equal to VI. But when the VI is greater than or equal to 2 volt, greater than means negative portion is greater, diode is off. When the diode is off, it will act as open circuit. When the diode is open circuit, output is what? VR. Output is exactly equal to VR. That is called clipping because it is independent of the input. Means when the VI is greater than 2, it will cut. When the VI is less than 2, it will pass. So if the clipping is below some reference level, this is called negative clipper, and if the clipping is above some reference level, then it is called positive clipper. So now tell me, what is the name of this clipper, everyone? This is the reference level 2. If this is the less than 2, output is exactly replica of the input. Greater than 2, output is constant 2. Means this portion is clipped. And that's why it is called positive clipper. Just opposite to that. That's why it is called positive clipper. Positive series clipper. Okay. So that is the value. Remember that. Remember that. And when we are changing the polarity, yes, Subham Sri, it is clear. Why it is called positive? Because it will cut the portion above some reference level. It is also called peak clipper or positive clipper. When it will cut the portion below some reference level, then it is called negative clipper. To change the polarity of the diode, it will become negative clipper. Okay. Next one. Clamper. Clamper simply used to add DC signal. It is also called DC restorer or DC inserter. So what is the purpose of the clamper, everyone? I will give only 2 diagrams. All the question based on what that 2 diagram. One is called positive clamper, another one is called negative clamper. Okay. So please share the link of this session. Everyone please like the session. Right. It is a quick revision. So there are 2 types of clamper. Positive clamper and negative clamper. It is also known as DC restorer, DC inserter or clamp capacitor. Positive clamper and negative clamper. I will give you only 2 formula for that. First, watch this. Here we are using one capacitor. Here we are using one diode, and here we are using one reference level. That is the basic diagram of the clamper. And here we are connecting the RN. Diode, VR, capacitor, VI. Right? Now, all questions depends upon this value only. Remember, I am giving you shortcut. First of all, watch the arrow. The current will flow in the downward direction. That is the downward. This is the positive. The current will flow in the P to N, and that's why it is a negative clipper. Negative clamper. Second thing, swing of the output is always equal to the swing of the input. Swing will remain same. Swing means maximum minus minimum. Maximum minus minimum. Swing will remain same. And what is the VR? VR will set a reference. VR will set a reference. So what is the meaning of this? Try to understand this concept. Very, very simple one. Directly you can give the answer for this question. For example, if I am giving one input signal like this. Okay, that this is a signal. And let this is the 10, 0 and what, minus 10. 10, 0 and minus 10. So first of all, it is a negative clamper. Second thing, let it is VR, reference voltage, and let this is the 2 volt, positive 2 volt. Positive, this is the positive, and negative, it is a 2 volt battery. Swing. So what is the swing of the input? 20 volt. The swing will remain same. Means what will be the output? First of all, draw the line here. Highest level will be the reference level. What is the reference level here? 2R. So this is the reference level 2. And the swing is 20. And that's why the lowest level will be 18. Lowest level will be minus 18. Swing is 20. Now you can draw the waveform like this. And that is the output. Finished. So this is a negative clamper. The swing will remain same and the output is clamped at 2 volt. That will be the output. That is over. Negative clamper. Then what will be the average value? Everyone give me the answer. What is the average value of the output or DC value of the output? What is the DC inserted by the capacitor, by this circuit? DC insertion. So always remember, when we want to calculate the DC or average or common value, add these two. 2 plus minus 18 divided by 2. That is minus 16 by 2. That is the minus 8 volt. Minus 8 volt is the average value for this. From this point to this point, the gap is 10. From this point to this point, the gap is what? 10. This is the average value. This is the value. Okay. Minus 8. Yes. Very true. So this is the question. What is the name of this circuit? Negative clamper. The output is clamped at 2 volt. What will be the swing of the output? That is similar to the swing of the input. And what is the average value of the output? You can calculate the average value of the output. Similarly, second clamper is positive clamper. Simply change the polarity of the diode and that is connected here. That this is the VR, this is the C, this is the VI. This is the positive clamper. Okay. If we are giving the same type of input, 10, minus 10 and 0, then what will be the output? I am directly giving you the output. First of all, draw the reference level. What is the reference level here? 2 volt. Reference level is 2 volt. Remember, right? First of all, draw the reference level 2 volt. Second, what is the swing? Swing is 20. 10 minus 10, that is the 20. So 2, highest level is 22. Highest level is 22. And that is the swing and that is the output. And so on. So this will be the output. So that reference level may be, if suppose I am changing the polarity of the battery, then it will become minus 2. Then what will be the answer? First of all, watch the diode. It is in upward direction, positive clamper. I am changing the polarity of the battery. Then no doubt it is given as 2, but it is the change of the polarity. It is actually minus 2. Then first of all, draw the line. Okay. Then the reference level is minus 2 here. Not 2, minus 2. If the reference level is minus 2 and the swing is 20, so what is the highest level? 18. And then you can draw a waveform. It is common in positive clamper or negative clamper. So watch the polarity of the battery. This is very, very important. Round tube, it is clear. If the battery polarity is reversed, then it will become minus 2, but the swing will remain same. So what is the highest level? 18. In a positive clamper, it will be 18. In negative clamper, minus 2, minus 22 it will become. Now, average value, always remember, add the average 22 plus 2, 24, 24. Half of the 24 is 12. 12 is the average value. 18 minus 2, that is minus 16. 16 divided by 2, 8 is the average value. I think now it is clear, everyone. Change the polarity of battery. It will start from minus 2. From minus 2 to minus 22. Okay. And that is all about the clamper. It is over. It is all about the clamper. Two types of clamper. Positive clamper, negative clamper. Finished. Right. Now, one diagram that is called, what is the name of this diagram? Everyone please give me the name of this diagram. That is C2, this is C1, that is D1, it is D2. So if this type of diagram, if it is given in the question, right, then remember, this is a voltage doubler. Voltage doubler. So it is the arrow. So this is a positive clamper. And this is nothing but positive peak detector. Positive peak detector. So if the signal is given as Vm sin omega t, then here we are going to get the 2 Vm. That is called doubler. If we are changing the polarity of both the diodes, this will become negative clamper and this will become negative peak detector, and the output will become minus 2 Vm. Minus 2 Vm. This is called, both the diagrams are voltage doubler. Voltage doubler. Okay. Yes, voltage doubler. Round trip, your answer is correct. Now next one. So bias negative clamper, this is the negative. Voltage doubler. Two diagrams, first one, second one. Always remember positive clamper, positive peak detector. Negative clamper, negative peak detector. Negative peak detector. Okay. So for first analog part 1, analog part 1 for PDF I will upload on my Telegram channel, that is Electronics by Sanjay Rathi. Already I have shared the link with you. Please join that channel. And the password, it is a password protected. The password is operational. Password is what? Operational. Because already we have covered operational amplifier in that. So don't share the password. Simply all the student will watch the session and they will get the password. Operational amplifier already I have discussed. Operational amplifier in part 1. Okay. Now after some time I will share the password of analog part 2 PDF. This is just, it will help you, right? It is just like what short notes. For quick revision, these all the PDFs are important, and then I am giving you the idea about that, which formula is important, how to use this formula during exam, right? And that's why this session is very, very important for you. Next one, Zener diode. So that is the Zener diode, and that is the symbol for this. Once it is in breakdown region, it has the VZ, and RZ is called its dynamic resistance. If in a particular numerical, if the dynamic resistance is not given, you can take it what? 0 or IZK. This is called minimum knee current that is required for the breakdown. If it is not given in the question, again you can take it what? 0 IZK. That is called knee current. Now, this type of diagram. This is called VZ, breakdown voltage, and that is called IZK, knee current required for the breakdown. This is the I, that is the V, or it has some slope that is known as 1 by RZ. If it is very steep, slope is infinite, then resistance will be 0. If in any numerical IZK is not given, then you can take it as a what? 0. It is an ideal condition. Now, voltage regulator by using Zener diode. That is again a very, very important topic. We will discuss voltage regulators by using Zener diode, then by using BJT, series voltage regulator, shunt voltage regulator, and there are again integrated chip type voltage regulator. One is called 78 series, one is called 79 series. So in case of 78 series, if it is written as 7805, then it will provide you the +5 constant voltage. Or if it is written as 7905, it is the number of this chip, it will provide you -5 constant voltage, -5. So that is the integrated chip voltage regulator, but we will discuss using Zener diode and by using the BJT, because we are having number of questions on that, as well as voltage regulator by using op-amp. Okay guys, ready? Yes, please. And this session will be up to what, 12. So please share the link of this session, everyone. Now voltage regulator. Next one, first of all, Zener diode as a voltage regulator. So here we are connecting one limiting resistor, that is R1 or RS, sometimes it is written as RS series resistor. Here we are connecting a Zener diode parallel to the RL. This is the standard circuit for voltage regulator. Here RL is variable as well as VI is variable. In some question VI is constant, RL is only variable. In another question RL is constant, VI is variable, or in some questions both are variable. VI or RL are variable. Siba, the PDF will be available on my Telegram channel, that is Electronics by Sanjay Rathi, after the class. Okay, tomorrow morning you will get the PDF. Now this is the R1 and that is the RL. Zener diode is a voltage regulator. Now, what are the important formula related to that? First, with these two formula you can solve any type of questions. Okay guys, this is the current I. 1 minute. First, this is the current I. This is divided into two parts. One is IZ, one is IL. VI. Always remember, Zener diode should be in breakdown region. Once it is in breakdown region, the voltage at this point will become VZ. What are the formula related to that? Then regulated voltage will become VZ first of all. Second thing, formula remember, I is equal to VI minus VZ upon R1 or RS. And this current is divided into two parts. One is what, IZ, and one is IL. Okay. Then first important formula on this. You can write IZ is equal to I minus IL. Yes. So what is the IZ minimum? Then IZ minimum is given by I minimum minus IL maximum. IZ minimum is given by I minimum minus IL maximum. Always remember, the minimum Zener diode current should be greater than or equal to IZK. That is called knee current. It is very, very important so that the Zener diode will remain in breakdown region. So that is one important formula. How we can write the I minimum? So I minimum is nothing but VI minimum. This is the VI minus VZ. So VI minimum minus VZ upon R1. How we can write the IL maximum? Directly you can write IL maximum, or we can write V0 upon RL minimum. When the load resistance is minimum, this is variable, then IL will become maximum. V0 is nothing but Vz. It should be greater than or equal to Izk. With the help of this formula, you can get the value of Vi minimum if everything is given, or what is the value of R1 you can find, or you can find RL minimum, and this is the formula. Izk, it will be given in the question. If it is not given in the question, ideally you can take it what? 0. That is one of the most important formula that is on voltage regulator. Next one. Next is same Iz maximum. Iz maximum is given by I maximum minus IL minimum. I maximum minus IL minimum. What is the I maximum? Vi max minus Vz upon R1. This is the when it is the maximum. It is fixed. Then you are going to get the I maximum. And from I maximum, when it is minimum, then you are going to get the maximum current through the Zener diode. Minus IL minimum. What is the IL minimum? V0 upon RL maximum. That is, it should be less than or equal to IZ rating. IZ rating. In particular numerical, they will provide you, in particular network, in a numerical, they will provide you the rating of the transformer. That is the maximum rating. Or otherwise, you can find the IZ rating. That is the maximum current. PZ rating. Power rating of the Zener diode is given in the question upon Vz. Because power is equal to Vz into Iz. If suppose 50 milliwatt rating is given, divided by Vz, you will get the Iz rating. This formula is very, very, very important in a gate exam. But remember one thing. What is the minimum value of the current? What is the worst condition? Worst condition is, worst condition. Sometimes we have to solve like this. RL is removable. We can remove the RL. When we are removing the RL will become infinite. When RL will become infinite, the IL minimum will become 0. IL minimum will become 0. So sometimes we have to solve the question with this condition. Remove this, IL minimum will become 0, and then solve this question. So only two formula sufficient to solve the question on voltage regulator, and this is a very, very important topic for all the branch. 5-star rating. Okay. So this is about voltage regulator. Now, next one. One minute. I will discuss the another type of voltage regulator. First of all, this is a shunt voltage regulator by using transistor. Shunt voltage regulator by using transistor. Then shunt voltage regulator means the transistor is connected in parallel with RL. Then it is called shunt voltage regulator. If it is connected in series, for example here this is the RL and it is connected in series with the RL, then it is called series voltage regulator. Shunt voltage regulator and series voltage regulator. So remember, in case of shunt voltage regulator, first of all, what are the important formula related to that? First, in case of shunt voltage regulator, normally this RB is not given. You can remove this RB. Then important formula, it should be in breakdown region, transistor should be in active region. So this is the Vz, that is the Vb. So first of all, V0 is equal to V naught is equal to Vz plus Vb. That is called regulated output voltage. Second, current I. I is Vi minus V naught upon 20. That is the RS. I minus. And this current is divided into Iz and Ic plus IL. No doubt here RL is not given, it is removed. But if the RL is given, then it is divided into three parts. Iz plus Ic plus RL. Now, if one question they may ask, only in the case, sir, voltage regulator only in case of breakdown region? Yes. For proper functioning of the circuit, Zener diode should be in breakdown region and BJT should be in active region. Right? That is the condition for voltage regulator. Otherwise, circuit will not work properly. Okay. Then directly, they will ask about the power dissipation. If they will ask about the power dissipation, always remember you have to use the maximum Vi. Power dissipation across the transistor and power dissipation across the Zener diode will be maximum when the complete current will pass through this and that. In that case, make the RL is equal to infinite and IL will become 0. And this current is divided into two parts only, Iz and what? Ic. You have to take the maximum value in this case, maximum. So what is the maximum? Imax. Imax is nothing but Vi max minus V naught upon R1 or RS. V naught is nothing but Vz plus Vb. Then this Imax is divided into Iz and Ic. Iz plus Ic. Remember, this Iz is nothing but Ib. Iz is nothing but Ib, and what is the Ic? Beta Ib. So it will become Ib plus beta Ib. From that you can find the Ib. What is the base current? I maximum divided by 1 plus beta. Once you will get the I base current, you can find the Iz because Iz is equal to I base current, or Ic is nothing but beta times of Ib. So what is the power dissipation across the transistor? Power dissipation across the transistor is nothing but VCE, or VCE is nothing but V naught. VCE and V naught. V naught is Vz plus Vb. So power dissipation across the transistor, it is given by VCE into Ic. And power dissipation across the Zener diode is given by Vz into Iz. Finished. Question finished. V naught is equal to Vc. Get the maximum. Always remember, when we are calculating the power dissipation, you have to find the maximum current. So that is, normally in this diagram, they will ask what is the power dissipation across the transistor, what is the power dissipation across the Zener diode, and regulated voltage Vz plus Vb, and that is the relation between Iz and Ic. That is the question. Okay. If you have any doubt, then you can ask. Next one. Series voltage regulator, this one. In series voltage regulator, again they will ask what is the power dissipation across the diode or transistor and diode, Zener diode. Vc. This is the Ic and this is IE. This is IB. Normally beta is not given, beta is very, very large. This is the Zener diode. It should be in breakdown region. It should be in what? Active region. And that is the V naught. That's why the V naught will become Vz minus Vb. Write down the KVL from this point to this point. V naught is equal to Vz minus Vb. That is the V naught. That is called regulated voltage. Independent of Vi, independent of RL. Then IE will become V naught by RL. IE is nothing but IL. It will become V naught by RL. Once you will get the I, V naught by RL, and this is nearly equal to IC because base current is negligible, then IC into VC, that will give you the power dissipation, VCE into IC. If the beta is given, then you can find the alpha, beta upon 1 plus beta. Then remember, IC is equal to alpha I. In this way, we can find the IC also. So I is equal to V naught by RL, and IC you can find. Now, remember this current. This is the current IR. This current is divided into two parts, IB and IZ. IB and IZ. If you want to get the power dissipation across the Zener diode, then you have to find the IZ. First of all, find the IR. IR is nothing but VI minus VZ upon R. This is called R. VI minus VZ upon R. Always you have to use the maximum here. Why maximum? Because it will give you the maximum power dissipation. First you will get the IR. IR is equal to IB plus IZ. IR is equal to IB plus IZ. Then how you can get the IZ? My dear, we have IE, or IE is nothing but 1 plus beta times of IB. 1 plus beta times of IB. From this formula you can find the IB. From this formula you can get the IZ, IR minus IB, and from the power dissipation formula, that is the PZ is equal to VZ into IZ, you can find the power dissipation. This is all about this diagram. This is all about this diagram. Okay. This is a voltage regulator, series voltage regulator. So, some student will ask, sir, we are not removing the RL here. If suppose you are removing the RL here, the current will become zero. Then there will be no power dissipation. So, in case of series voltage regulator, RL should be what? Minimum. If the RL is minimum, then there will be the maximum current. Then there will be the maximum power dissipation. Or in case of shunt voltage regulator, RL should be maximum. Maximum means infinite. So that is the difference between shunt voltage regulator and series voltage regulator. It should be minimum here. Then if it is minimum, then maximum current will pass. If this is maximum, IC will be maximum, then IB, then IZ. If suppose you want the IZ maximum, always remember, if you want the IZ maximum, what will be the condition, everyone? If you want the IZ maximum, then IB should be minimum. If you want the IB should be minimum, then IE should be minimum. If you want the IE should be minimum, means RL should be infinite. So there are two worst conditions. In a GATE exam, they will give you this type of questions. Find the maximum power dissipation across the transistor. In that case, RL should be minimum. Find the maximum power dissipation across the Zener diode. In that case, RL should be infinite, IB will become zero. The complete current will pass through the Zener diode, then there will be the maximum power dissipation. Or in both the cases, you have to put the VI is equal to what? Maximum value. So this is a very, very conceptual thing. If you find any difficulty, then write me on the comments box. Okay. Now, this is the voltage regulator by using op-amp. Means here we are connecting the 12 volt battery or any VI, that is the variable battery VI. It is a one question from the GATE exam. Here we are connecting the Zener diode. It should be in breakdown region. It should be in active region. And this operational amplifier should be with negative feedback so that virtual short concept is valid. Virtual short concept is valid. So if it is of VZ, then VP is equal to VZ, VN is equal to VZ, and therefore the voltage at this point is VZ. And what is the current enter into the operational amplifier? 0, because its input resistance is infinite. Then you can find the V0. What is the relation between VZ and V0? If let this is the R1 and this is the R2, R1 and R2, then we can say VZ is equal to, according to voltage divide rule, R2 by R1 plus R2 into V0. R2 by R1 plus R2 into V0, that is equal to VZ. So what is the V0 is equal to? R1 plus R2 divided by R2. into Vz. That will give you the regulated output voltage. So remember, they will ask this type of question. If it is the Vz, what will be the output, right? And from the output, you can find the current through this R1 and R2. You can find the current through the RL. Normally RL is connected here, but the value of RL is very, very low. It is in the range of what ohm. These are connected in kilo ohm. Very large current flow through the RL. You can find the IE. IE is normally nearly equal to what? IL. Once you will get the IE, you can get the power dissipation across the transistor. What is the power dissipation across the transistor? VCE into what? IC. And IC is nearly equal to IE. VCE, unregulated voltage minus regulated voltage. VI minus V0. IC is nearly equal to IE. So these are the formula related to this diagram. Only this type of questions they will ask. Okay, if you find any difficulty, then please ask me. Yes, please. Okay, so normally they will give you the RL. So V0 by RL plus V0 by R1 plus R2 will give you the value of IE. But V0 upon R1 plus R2, V0 upon RL, that will give you the value of IE. But this is a very, very large because it is in the ohm and this is in the kilo ohm. And that's why IE is nearly equal to what? V0 by RL. Once you will get the IE, IC is nearly equal to IE, and you will get the power dissipation, that is the VCE into IC, and VCE is nothing but VI minus V0. Always remember, when we want to find the power dissipation, you have to use VI maximum. It will give you the worst condition. Okay, that is all about this question. Now, hybrid pi model including what? Early effect. Okay, so ready guys? So now we are going to start what? BJT. BJT. It is a curve is elevated. Curve is elevated because of what? Early effect. This is called early voltage. When we are extending the curve backside, all the point will merge at this point, and that is called early voltage minus VA. VA is called early voltage. With the help of early voltage, we can find the slope of this line. And once we will get the slope of this line, we can get the R0, output resistance. And output resistance is given by VA by ICQ. VA upon ICQ, VA is the early voltage and ICQ is the quotient current, collector current. Now the collector current in general, without early effect, the collector current is given by I0 e raised to power VBE upon VT. Normally eta is 1 for transistor. I0 is the reverse saturation current. VBE is the applied voltage across the transistor. That is called VBE. NPN transistor, this voltage is called VBE. This is forward bias by VBE. If it is known, then directly you can find IC. IC is nothing but I0 e raised to power VBE upon VT. If we are considering the early effect, then this formula is multiplied with 1 plus VCE by VA. VCE is the voltage across this point. So if we are considering the early effect, it should be multiplied with 1 plus VCE upon early voltage, that is nothing but VA. And that's why the current will increase. That is the effect of early effect or base width modulation. Right? Remember that formula. First effect. Second, hybrid pi model including early effect. So this is a very, very important one to solve the question based on what? Mid-frequency analysis. Mid-frequency analysis. So this is a GM V pi, this is the R pi, this is the GM V pi, and just I want to give idea about that R naught. R naught is called output resistance, that is based on early effect. This is the VA by ICQ. Okay. Before entering into the low frequency analysis, mid and high frequency, first of all, biasing and stabilization. What is the meaning of the biasing and stabilization? First of all, so that is, you got the idea about the early effect. Now, something about the BJT. First of all, watch this first. In a BJT, that mode of operation, we are having the two junction. One is called emitter junction, one is called collector junction, and we are having different modes of operation: cutoff, active, reverse active, and saturation. In cutoff, both the junction reverse bias. In active, forward bias, reverse bias. In reverse active, emitter junction is reverse bias, collector junction is forward bias, and in saturation, both the junctions forward bias. Cutoff and saturation, that is extreme end of the characteristics, are used for switching action. Normal active mode is used for amplification of the signal, and reverse active mode is rarely used for low amplification. If suppose in some cases low amplification is required, then reverse active mode, rarely used configuration or mode of operation. So that is the cutoff, active, reverse active, and saturation mode. These are the different modes. Now, early effect, as you know already, I have given the early voltage. This is called base width modulation. So definitely there will be a 1 or 2 question on base width modulation or early effect. Right, already I have given the formula for the or not. Now, because of the early effect or base width modulation, what will happen? First effect, W depletion layer increases, effective base width decreases, recombination decreases. But for analog, remember, recombination decreases means alpha increases, or when alpha increases, IC increases. First effect. Second effect, base current, recombination current decreases. Third, emitter current increases because it is a diffusion current and concentration gradient increases. Right? So that is the early effect. That is important for analog. In case of early effect, emitter current increases, collector current increases, but base current decreases and alpha increases. Alpha increases. Now, there are different types of configuration here. So some students saying that, sir, if particular terminal is ground, then we can say it is a common base or common emitter or common collector. No. You have to watch the input and output. We are having the 3 terminals: base, emitter, and collector. If we are giving input to emitter, this is the input is given to emitter and output from the collector, then it is called common base. This is the common base. Right? If suppose if we are giving input to the base and output from the collector, then it will become common emitter. And third case, if the input is given to the base, output is from the emitter, then it will become common collector. You have to check only input and output. Input and output terminal, according to which we can say it is a common emitter, common collector, or common base. So what are the properties of the common base? First, lowest input resistance, highest output resistance, lowest current gain, that is the alpha only, IC by IE, highest AV, moderate power gain, phase shift is 0, common base amplifier will offer largest bandwidth. It will offer the largest bandwidth and it is more suitable for high frequency application. So these are the important points. These are important for MSQ or 1 mark question. Property, comparison, right? So these are the property of the common base. Application, they may ask as a constant current source. Remember, IC is equal to alpha I. It is a current controlled current source, constant current source, non-inverting voltage amplifier. The phase shift in this case is what? 0. That's why it is non-inverting. Second thing, the voltage gain is highest. That's why it is used as voltage amplifier. Third, as a high frequency amplifier. Already I have given the bandwidth is very high, and between impedance matching device between low resistance and high resistance. Remember, its input resistance is low, Ri is low, and output resistance is high, that is in the range of what? Mega ohm. When there is a matching is required between low and high resistance, then it is used as a buffer. It is used as a buffer. Okay. That is about the common base configuration. Important points. Second one is common emitter, most popularly used configuration because its power gain is highest among the three configuration, whether it is a common collector, common emitter and common base. Second, we are giving input to the base, output from the collector, common terminal is emitter, most popularly used configuration. And then this is the with the PNP transistor. This is with the NPN transistor. Its input resistance is moderate, output resistance is also moderate, AV high, not very high, current gain is high, but power gain is the highest. Phase shift is 180 degree. Most common and very popularly used configuration. Okay, that is about the common emitter. Finally, common collector. Watch this. We are getting the output from the emitter and we are giving input to the base. That collector is not grounded. A DC voltage is connected here. It is no doubt AC grounded, but DC voltage is connected. So simply watch the output terminal. Emitter is the output, base is the input, and that's why it is a common collector. It is also called emitter follower. Emitter follower. Common collector means. Right? Emitter follower means the gain, voltage gain is nearly equal to 1. Output will follow the input. And we are getting the output from emitter terminal. And that's why it is called emitter follower. Now, what are the properties of the common collector? Input resistance is highest among three configuration. It has the highest input resistance. Second, lower R0, the highest input resistance is given by Ri is equal to, the general formula is Hi plus 1 plus HFE into Re. So mainly the input resistance is high because of this term, 1 plus HFE into Re. That is called feedback resistance, Re here. This is nothing but RL or Re. Because of this resistance, the input resistance is very, very high. Lowest R0, very, very low. Highest current gain. And phase shift is 0. And voltage gain is nearly equal to 1. And that's why it is called emitter follower. Remember, the current is, output current is I is equal to 1 plus beta times of IB. And that's why the current gain is what? 1 plus beta here. Highest current gain among three configuration. For common emitter, the current gain is beta. And for common base, IC is equal to alpha I. Current gain is alpha. Here beta. Here it is 1 plus beta. Common collector. Common emitter, common collector. This is the common base. Okay. So these are the important formula related to three configuration. Now, properties and so on. Common collector configuration. So in a table it is available. Please take a screenshot of this, or PDF will be available on my Telegram channel. Right? The password for this PDF I will share with you. Okay. Then this is the all the property of common base, common emitter and common collector. You can check, already I have discussed all the property, all the applications and so on. Now we will enter into what? Biasing and stabilization. That is the DC load line concept. Right. DC load line concept. What is the DC load line concept? This is the characteristics of the common emitter without early effect, because it is not elevated curve. This is the common emitter characteristics. Here we are giving the IC. The maximum value is VCC by RL. Minimum value is 0 almost. This is called DC load line. This is the DC load line. And this is called Q point. Right? The one question they will ask, if suppose that is the diagram, this is only given RC. And this is the VCE. This is connected to ground. What is the slope of the DC load line for this diagram? They will ask. Then always remember the slope of this is the negative, and the slope of this DC load line is minus 1 by RC. Minus 1 by RC. Intersection of this point and this characteristics is called what? Q point or operating point, and it should be, normally it should be in middle of active region. This region is called active region, and it should be in the middle of the active region. For maximum swing at the output, for minimum distortion at the output, that Q point should be in the middle of active region. That is the reason, the Q point. This Q point is not stable, right? So what are the points? Because of that, this point is important. The slope of the DC load line is minus 1 by RC. Now, Q point stability is affected due to, that will be the question. First point, why the Q point is not stable? Sir, what if it is not at the middle? If it is not at the middle, definitely you will get the output, but with what? Distortion, or the swing will not be maximum. Normally we are using the audio frequency amplifier or RC coupled amplifier. In that case, it should be at the middle of the active region, so that we are getting the maximum swing. Okay, and output without any, output with minimum distortion. So why the, if suppose we want to set, then we are setting the Q point at the middle. We are setting the Q point at the middle of the active region here. Then the factor affecting the Q point is first temperature. A temperature has two hands, right hand and left hand. It is a dawn, so it is a right hand, it is the left hand. So what is the right hand? ICO. ICO means reverse saturation current, or it doubles for every 10-degree rise in temperature. So definitely it will affect the Q point. It will affect the Q point. This is the IC, this is the VC. So always remember IC is equal to beta IB plus 1 plus beta times of ICO. So if the temperature increases, what will happen? ICO increases. The temperature increases, ICO increases, and therefore IC will also increase. But always remember, VCE for this diagram, VCE is nothing but VCC minus IC into RC. That is the general diagram. Temperature increases, ICO increases, IC increases, but VCE decreases, and Q point is moving upward from this point to this point. This point, and it will enter into the saturation, because this region is saturation and that region is what? Cutoff. And once it enter into the saturation, the transistor will stop working like an amplifier. That is the problem. First problem they will ask. Second problem is VB. It is also changed with the temperature. That is, what is the rate of change? dVB by dt is minus 2.5 millivolt per degree centigrade. Or beta is highly affected due to replacement of the transistor. When we are replacing the transistor, means when we are changing the transistor, then the beta is highly affected. That is a very, very important relation, a very important point for Q point stability. Okay. Yes. The equation of the line is y is equal to mx plus c. Yes, you can say that is the DC load line. It is highly affected. That is, these are the reason. So first is temperature, ICU and VB. Second is what? Replacement of the transistor. Beta is highly affected. That there may be MSQ on that. No. Now, what are the meaning of the stability factor? There normally there will be the question on stability factor. So there are three types of stability factor. One is called change in IC because of change. There are three villains, remember. One is ICU, another one is VB, another one is what? Beta. First of all, keep these two constant, and what is the variation because of ICU? That is called stability factor S. Change in IC because of change in ICU. When the beta and VB kept constant. This is a very, very important formula. Then what is the S dash or SV? Change in IC because of change in VB. This is also known as SV. And third is S beta. Change in IC because of change in beta when VB and ICO kept constant. There are three factors: ICO, VB, and what? Beta. We are having S, S dash, S double dash here, or S double dash is also known as S beta here. S beta, beta factor. Okay. Sir, when it enter into the saturation, always remember transistor should be in active region. If it is in active region, then it behaves like what? An amplifier. Once it enter into the saturation, there will be the change in the input, but there will be no change in the output. Are you getting my point, round tube? If suppose you enter into the saturation, I am giving you the content, but you will not get the concept here because already you enter into what? Saturation. That is the problem. The signal will not get amplified. Okay then. S, S dash, S double dash. Now, this is the stability factor. Circuit is not stable. To make the Q point stable, we are using the different types of techniques. What are the techniques? Stabilization techniques. Stabilization technique is divided into two parts. One is called biasing technique and one is called compensation technique. In biasing techniques, we are using two types of biasing. One is called collector based bias circuit, another one is called self biased circuit. So normally we are getting the question from the self biased circuit. This is also important: collector based bias circuit, self biased circuit. Or in compensation technique, we are using the diode compensation, transistor and thermistor compensation, and transistor compensation. One by one I will give you the diagram. What is the collector based bias circuit, cell bias circuit, and diode compensation, transistor and thermistor compensation. Now, biasing compensation technique. This. Okay, so that is the diode compensation. First of all, if RE is given here, that is called self-biased circuit. No doubt sometimes that potential divider is connected here. So that's why it is called potential divider bias circuit. It is another name of this. Right, this type of circuit, it is called potential divider bias circuit, voltage divider bias circuit, emitter bias circuit, or self-biased circuit. This is the standard circuit here. Right. And then stability factor is nearly equal to 1 plus RTH by RE. 1 plus RTH by RE, where RTH is nothing but R1 parallel with R2. Remember that stability factor for this circuit. This is a very, very important one. Okay. Then second one, if simple circuit is given here and simply we are connecting one RB between collector and base. Then this type of circuit is called collector based biased circuit. Biased circuit. This is a collector based biased circuit. Then third one, these are the two important circuit. Third one is normally known as what? Fixed bias circuit. But that is not a technique. If there is no negative feedback, then circuit is called fixed bias circuit. This is an unstable circuit. This is the fixed bias circuit. Here we are connecting a very simple battery here. This type of circuit is called fixed biased. No negative feedback. No RE, no collector based biasing. Then it is what? Fixed biased circuit. And this type of circuit or this type of circuit, this is also a fixed bias, no negative feedback, no RE, no collector based biasing. This is also a fixed bias circuit. Only this is connected. So all are fixed bias circuit. There is no negative feedback, and the stability factor for all this circuit is 1 plus beta, very high. Or already I have given stability factor is change in IC because of change in ICO, with the VB and beta kept constant. So this is a very high value, right? Or if when we are giving the negative feedback, S will become less than 1 plus beta. S will become 1 plus less than 1 plus beta, then the circuit is stable. Okay, so that is the formula. Right. Next one is compensation technique. Refer to use of temperature sensitive device such as diode, thermistor, transistor and transistor. Okay, sir. Array, what is the use of that circuit? As a switch, my dear. If both the junction is forward bias, then it is used as a switch. Switch means what? There are two conditions. One is what? On condition, one is called off condition. That is bistable multivibrator. Or we are making flip-flops. In flip-flops, we want to get the two outputs only. One is called 0 and one is called 1. So in saturation mode, transistor will act as short circuit, output will be 0. Or in a cutoff mode, output will be 1. These are called two extreme case. Output will be 1. In saturation, output is 0. In cutoff, output is 1. 0 and 1, binary number. If you want to design the flip-flop or binary, then we are using the cutoff and saturation mode. That is for switching. Okay. So in a compensation technique, this, if the diode is connected here, diode is connected in this path, or RE is also connected, means it is a cell biased as well as when extra diode is connected, then what will be the question? Why we are connecting the diode here? Because to reduce the effect of variation in VB, that will be the question. So this is the diode compensation, and when we are connecting the diode at this position, that is especially to compensate the effect of VB. That will be the question. Effect of the VB, and this is important for silicon transistor, because in case of silicon transistor, the effect of VB is very high. That circuit is useful for silicon transistor. If suppose the diode is connected here, watch this diagram, diode is connected here in place of R2, then this is called diode compensation for ICO, that is reverse saturation current. And this is more important for germanium transistor. Why? In case of germanium transistor ICO, the effect of change in ICO is very high. That's why we are connecting the diode here. That is called diode compensation. Now, next one is what? Thermistor and transistor compensation. Thermistor means it is a lightly doped semiconductor material, or transistor is highly doped semiconductor material. It has negative temperature coefficient of resistivity. Means temperature increases, resistivity decreases, resistance decreases. It has positive temperature coefficient, just like a metal. resistance increases. And there is one question only on this diagram, my dear. Here we are connecting RE. Remember this diagram. RE is known. If suppose you want to replace, this is the RC, we can't replace it. If you want to replace this transistor, this resistor, we are connecting this resistor. This is RT means thermistor. It is a thermistor. RT means thermistor and RS means sensistor. Let. That is the thermistor. Right? If you want to replace then RE, then we want the temperature increases, this resistance will increases. That is what sensistor. So that there will be more negative feedback and circuit will be stable. Then right, we can also replace this R1 and that R2 also, right? So this above, this one is sensistor. If you want to replace R1, then you have to replace it by sensistor. Or this is the R2. If you want to stabilize the circuit, you want to replace, then it should be replaced by what? Thermistor. Sensistor and thermistor. So this is thermistor. That will be the question. This is emitter resistance is sensistor. It should be replaced by what? Sensistor. It should be replaced by what? Thermistor. So that is called thermistor and sensistor compensation technique. No doubt they will not ask you the value and so on. They will ask you what is the replacement. So R1 is replaced by sensistor. R2 is replaced by the thermistor. RE is replaced by the sensistor. RT is this is the thermistor. We have the reason for that, but it is a Formula 1 series. Formula 1 series means concepts and formula only, right? What are the values and so on. So I can't explain each and everything. It is not possible to explain each and everything within 2 hours. But brief idea about all the topics, what are the important and so on. If you find any difficulty, then give me comments, right? On on comments box as well as on my Telegram channel, that is Electronics by Sanjay Rathi. Okay. So that I will arrange session for that. If suppose you find difficulty on this topic, so you can write me the comments that sir, sensistor and thermistor. Take one session on sensistor and thermistor compensation. Take one session on what? Cell bias circuit or collector based bias circuit. Okay. So definitely I will try to arrange those sessions. These all are the important topics from the analog. First of all, go through this. Now, this is the diagram for what? Transistor compensation, my dear. This is a very, very important diagram. So, normally in a GATE exam or in other competitive exams, they may ask one numerical on that. This is a very, very important numerical from Milman Halkias. Just I am giving you the brief idea that these are the two transistors. If this type of connection is there, this is called transistor compensation. Means to compensate or to stabilize this transistor Q2, we are connecting one extra transistor here, Q2 and Q1. There are two transistors and that's why it is called transistor compensation. In IC fabrication, normally we are using this. So this is a highly stable circuit. Highly stable circuit. So one numerical they may ask on this diagram. This is a standard diagram to try to solve this numerical. That is from Milman Halkias unsolved numerical. Now already we have discussed the voltage regulator by using the BJT and by using the operational amplifier. Now after biasing, frequency analysis of BJT. Frequency analysis of BJT. First of all, frequency analysis means remember, for RC coupled amplifier we are having this type of curve, frequency response curve, that is called. Here on x-axis we are having the frequency, on y-axis we are having the gain. So we are having this type of response, that is called frequency response curve. right? Now here another one, this is called low frequency region and this is called high frequency region. This is called higher cutoff frequency, this is called lower cutoff frequency, right? And this region is called mid frequency region. What is this? Mid frequency region. In a mid frequency region, the gain is almost constant, independent of the frequency. There is no variation, almost constant. But at high frequency, there is a fall in the gain. High frequency, there is a fall in the gain. Okay, right. Or at low frequency, there is again the fall in the gain. This is when we are decreasing the frequency, the gain will reduce. So this is called cutoff frequency and that is called the cutoff frequency. Higher cutoff frequency, lower cutoff frequency. And this is called bandwidth, FH minus FL. FH minus FL. So this is just like a band pass filter. The first question, why we are getting this type of structure? Why we are getting this type of structure or this type of frequency response curve? Gain, magnitude of the gain versus what? Frequency, right? So they will ask the question, why the gain will fall at the high frequency region and why the gain will fall at the low frequency region. Remember, this is the circuit, very standard circuit. This is called audio frequency amplifier, RC coupled amplifier. This is the RC, this is the VCC. Here we are having one capacitor. Now, before input we are connecting one capacitor. Before output we are connecting one capacitor. Before giving the input, this is the capacitor, and here we are giving the input. And here we are getting the output. These are called coupling capacitor. This is called bypass capacitor. Or since the emitter junction is forward bias, in active region emitter junction is forward bias, and that's why diffusion capacitance. When the junction is forward bias, there will be the diffusion capacitance, and collector junction is reverse bias, then there will be a transition capacitance. So internal capacitance are called diffusion, transition, wiring capacitance, or other stray capacitance. Number of unwanted capacitances are there. These all are the internal capacitance. They are not visible here. Diffusion, transition, wiring, stray capacitance, and so on. Or these are visible. We are connecting CC1, CC2 and C. These capacitors are very high. When we are connecting this, the value of this should be very high. Very high. And all these capacitors are very low. It is in the range of what? Picofarad normally. Or they are in the range of microfarad. 100 microfarad or 50 microfarad and so on. So these are the required value. First question, it is over. Second question, right? Now, second thing, why the gain fall at FH? Why the gain fall at higher frequency side? Higher frequency side, the gain decreases due to internal capacitance. That is the CD, CT, CW and CS. Remember that. CD, CT, transition capacitance, CW and CS. Because of the internal capacitance, the gain will fall at higher frequency. Means FH depend upon this parameter. Or gain at lower frequency fall because of external capacitance, that is called coupling capacitor and bypass capacitor. Coupling capacitor and bypass capacitor. Or in mid frequency range, the gain is almost constant. The gain is almost constant. So when we are solving the numerical, means when we are finding the gain or input resistance or output resistance, so normally we are finding all this at which point? Mid frequency region. We are finding the gain and all these things at the mid frequency region. Because in mid frequency region, the gain is almost independent of the frequency. It is a constant gain. So whether we are using the hybrid model or what pi model or what RE model, so normally we are finding the gain and each and everything, input resistance, output resistance, power gain, phase shift in mid frequency region. And that's why in numerical they will ask find the mid frequency gain. So when they will ask mid frequency, then gain, then no need to consider the CC1, CC2, and no need to consider the CD, CT and CW and CS. That is, you simply remove it. If they will ask what is the high frequency response, then you have to consider this. If they will ask what is the low frequency response, then you have to consider this. But remember one thing, at the low frequency side, it acts as high pass filter. And at the high frequency side, it acts as what? Low pass filter. At the high frequency side, it acts as low pass filter. The frequency increases, gain decreases, and that's why it is called low pass filter. Here the frequency increases, gain increases, and that's why it is called high pass filter. Here it acts as high pass filter, there it acts as low pass filter, and overall diagram acts as what? Band pass filter. Okay. Now, please give me next one. Okay. What is asked? Round tube, which is better, self bias or fixed bias? Oh, no doubt. My dear, if there is a high variation, extreme condition, there is a high variation in the temperature, high variation in the condition, then definitely self bias circuit is better. Why? Because in a self bias circuit, there is a negative feedback, and that's why the Q point is stable. But suppose there is no variation in temperature, everything is stable, then definitely the fixed bias circuit. Why? Because in fixed bias, there is no negative feedback. No doubt, the Q point is not stable. But my dear, when we are applying the negative feedback, the gain will reduce, cost of the circuit will increase. So self bias circuit is costlier than the fixed bias circuit. So if when we are comparing on the basis of stability, self bias circuit is more stable. But if there is no variation, then which circuit is better? Fixed bias, because there is no negative feedback, we are going to get the high gain. Are you getting my point? Yes, it depends upon your use. Next one. Now, this is the model. I am going to explain you the model, pi model and RE model and this one. First of all, this is the pi model. Remember that. That is pi model including the early effect means this is a simple R pi, GM V pi in E, and this is the R naught. Here, first of all, transconductance. You have to find the GM. GM is given by mod of IC by VT. Get the DC current and then VT, volt equivalent of temperature, that is nothing but KT by Q or T by 11,600. Exactly at 300 degree Kelvin, the VT is equal to 0.0259 volt, and that is nearly 26 millivolt, or exactly at 298 degree Kelvin, that is 25 degree centigrade, VT is nearly equal to 25 millivolt. Normally in GATE exam, VT is given as 25 millivolt. From that you can find the GM, then we can use this model, GM. And then you have to find the R pi. R pi means beta by GM. Beta HFE by GM or beta by GM. Then you can use the R pi connected here, GM V pi connected here, E is connected here, R naught. Or already I have given R naught is given by VA by ICQ. Early voltage upon ICQ, you can find the output resistance. So that is about the model. So in electrical branch, normally they will ask what is the GM, what is the R pi, and what is the R naught. Emitter is connected here, collector is connected here, base is connected here. This is the small signal model, linear model for BJT. Linear model. We are not connecting any capacitor. It is in a mid frequency region. It is in the mid frequency region. Okay. The next one. This is called T model. Small signal T model for BJT. Here in emitter terminal we are connecting the RE. This is the base terminal, GMVB, or sometimes this collector current is represented by alpha IE. Alpha IE also. That is also correct. GMVB is also correct. VB is nothing but voltage across base and emitter. Remember that. Now, if it is alpha IE or this is the RE, this is called RE model, small RE model, or what? T model. In this model, we have to calculate the RE. RE is given by VT by IE. VT by IE. Or that GM. Already we have GM is nothing but IC by VT. IC by VT. Or normally IC is nearly equal to what? IE. If in any numerical, beta is very large is given. Very large. If it is given, then the base current is 0. If the base current is 0, then IC is nearly equal to IE. So it is nothing but 1 by RE. That is the relation between what? Relation between GM and RE. We can use this type of shortcuts. Relation between this. So GMVB, this is the IB, this is the RE. So normally we are using this model, that is called small signal model of the BJT. So that is a small signal model, and these are the important formula related to that. Then sometimes they will ask about the Miller's theorem. They will ask about the Miller's theorem. So what is the Miller's theorem here? If suppose any diagram is given between 1 and between terminal 2, if any impedance is connected, for example, it may be capacitor or it may be inductor or it may be resistor. So it is impedance is given Z between 1 and 2, and you have the idea about the V0 by V1. Let the V0 by V1 is K. So it is connected between input and output. Then you can break this impedance into two parts. One is connected between input and ground. One is connected between output terminal and the ground. Then what will be the value? So that these two diagrams are equivalent. So according to Miller's theorem, if you want to break this, so at this point it will become Z upon 1 minus K, or at this point it will become KZ upon K minus 1. KZ upon K minus 1. That is the formula. Okay. So this is the KZ upon K minus 1. So we can break this impedance into two parts. But remember that if it is resistor, then that is the formula. R is equal to R upon 1 minus K. Here it will become KR upon K minus 1. If it is inductor, then again L upon 1 minus K, KL upon K minus 1. But if it is capacitor, then? If it is capacitor, then number of questions on capacitor. This is the capacitor. Now you can break this capacitor into two parts. We will have one capacitor here and one capacitor here. Then V1 and V2. If the K is given as V2 by V1, then we can break this capacitor. This will become C into 1 minus K. Or here C K minus 1 upon K. Just opposite to that what? Resistor and inductor. K minus 1 upon K. That is very useful to explain the concept of what? High frequency analysis. That is called Miller's theorem for capacitor. This is a very important one. Okay. Now we have to discuss more topics then, but we have to discuss what first of all oscillators, feedback amplifiers, okay, and important formula related to that what? MOSFET. Biasing and stabilization of MOSFET. So these are the important topics. Different types of feedback topology, that is voltage shunt, voltage series, current shunt and current series topology. Okay, so I will arrange an extra session for that. And then, so up to this point we have completed some topic. So what is the password for analog? Part 2. Part 2, remember that. Stabilization. Right, so that is the password. Correct the spelling, sorry. This spell, please note the spelling. So that is written here, then I will use the same stabilization techniques. Okay, so stabilization is the password for the STABLISATION. That is the password for the analog part 2 PDF. And then PDF will be available on my Telegram channel, that is Electronics by Sanjay Prathi. Right, guys. Now, tomorrow I have one important session, that is on electronic devices and circuit. Part 1. Electronic devices and circuit, sharp at 9 PM. And here we will discuss semiconductor physics, PN junction, diffusion capacitance, transition capacitance, everything about the PN junction, Fermi level, that is from the semiconductor physics, all the formula related to what? Semiconductor physics. Third, BJT, right? And then characteristics of the BJT, MOSFET, and then finally we will discuss special diodes. So electronic devices and circuits, EDC, that is a GATE Formula 1 series, sharp at 9 PM tomorrow. Okay, so please like the session, subscribe our channel and share the link of this session. Then thank you for attending the session. You are on BYJU'S Exam Prep. Okay, then thank you and good night.